Radian and degree measure. When did you get back, Kirsten? Kirsten, when did you come back?
New Year.
Oh, okay. So you've had a couple of days.
Yeah.
3 hours is a hard adjustment. Yeah, I get it. Okay, angles in standard position. Let's just talk about this real quickly. You should be drawing some sketches in your notebook so that you have an idea visually of what an angle in standard position looks like. The blue angle that I have there on the screen, that is an angle in standard position. Okay. In geometry class, you probably just had like angles in space. They weren't necessarily tied to the coordinate plane. When we move into algebra and pre-calculus, then we can say, okay, let's put them on the coordinate plane. Let's have them all be in the same location. This is called standard position. So in standard position, you have one side that is always the same. It's called the initial side. The initial side always starts on the positive x-axis. So if you think about u being a point at the origin, if you were to draw a ray to the right along the positive x-axis, that is always the starting or initial side of an angle. Okay? Then an angle can open clockwise or counterclockwise, and eventually it ends somewhere in a quadrant on one of the axes, and that side is called your terminal side. Think about the word terminal. Terminal, to terminate, would mean to end. Okay, so that's wherever your angle ends. And because I have drawn this little red arc, and I'll be looking for this in your angles as well, this angle is opening counterclockwise, okay, the opposite of how the clock moves. And this is a positive angle. Okay, so positive angles open counterclockwise. Just to kind of help you with counterclockwise and clockwise, if you have a hard time remembering which is which in terms of those words, if you are familiar with, and you should be, the numbers for the quadrants on a coordinate plane, so like this top right is quadrant 1, top left is quadrant 2, bottom left is quadrant 3, and bottom right is quadrant 4. If we're saying that it's positive, then it follows the order of the quadrants. So it opens quadrant 1, 2, 3, 4. That's counterclockwise, okay, or that's a positive angle. If you were to open in the opposite direction and follow the quadrants 4, 3, 2, 1, then you would be a negative angle. So write down negative angles, open clockwise. This way, if we all draw angles in standard position, then my angle will look like Blake's angle, whose will look like Bruin's angle, and we'll know we all have the same angle. Okay, so we're kind of standardizing what the angle looks like, so it's easier for us to look at and compare. If I draw a negative angle, I'm actually going to draw something that looks almost exactly like the angle that I have on the left. The only difference would be the arc, right? Instead of going clockwise or counterclockwise, I want to go clockwise. And so those are the same angles, so they would have different measures because one is opening to be positive and the other is opening to be a negative angle. Does that ring a bell from Algebra 2? How you talked about standard angles? Okay. Good. Yes, and I would definitely, we could say that right now. When we name angles, we'll use theta. Okay, mine looks like an O with like a little curl at the top. Okay, theta often in print, like in type, it might look like a 0 with a line through it. Okay, so however you prefer to write theta, mine is just like the cursive O because that's easier to write. Okay, but either one of those would be acceptable. Okay, radian measure, this for me is like a steal from Algebra 2. That's the first time you were introduced to radians. So like this is the same slide that I show my Algebra 2 students, that I show my pre-calc students, that I would show students beyond who are just kind of reviewing radian. So I'll give you a minute if you want to write down the definition of the radian. And then in a little bit, I'll talk about like the definition in conjunction with the animation that you see. If you are in Miss Fanchulo's or Mr. Griebel's class, I would say for sure you've seen the same animation. I'm not sure if all the Algebra 2 teachers, I'm trying to think who else taught Algebra 2 last year. Mr. Richmond? Anybody have Mr. Richmond? Do you know if you've seen this before? Okay, doesn't look familiar. So maybe you've seen it, maybe you haven't. Okay, so 1 radian is the measure of an angle in standard position whose terminal side intercepts the arc of length r, where r would represent the radius of some circle. Okay, so that's what the animation below is trying to show, and I'm going to wait for it to kind of start over, and then I'll talk about each part of the definition in terms of the animation. So if you're looking at the board, that would be a good idea right now. It's going to start over. We're going to draw a radius, and from that radius, we just move it around 360, we create this circle. Okay, we're going to take the radius and pull it outside of the circle. It has the same length. We're not going to change the length, but we're going to bend it to fit the circle. That's the arc of the circle. The green angle that fits that arc of the length of the radius is 1 radian. Okay, and then you can add to that 2 and 3 radians. Notice 3 radians is almost half the circle. 3.14 or pi radians is actually half of the circle, so it's equal to 180 degrees. Okay, and then if the first half of the circle is pi, then the other half of the circle is also pi, so 1 full revolution is 2 pi. Okay, so that's the idea behind the radian. The radian is another type of measurement. You have the degree, then you also have a radian. And you know, in different cases, you might choose one or the other, just depending. A lot of higher level math will use radians because the nice thing about radians is if it's in terms of pi, it's really a fraction of the circle. Okay, because you know the circle is 2 pi. And so the fraction tells you how much of that circle you actually have. 1 radian, and you can kind of tell in the picture, is close to like 60 degrees, but I think it's like 57 point something is actually 1 radian, and that's why you need a little bit more than 3 of them, 3.14 or pi, to get 1/2 of the circle. Okay, so just kind of be aware of that. It's good to kind of understand what the radian actually means. Here are some things that we want to talk about. So first thing is angle measure in degrees and radians. So, okay, I gave you the angle in standard position. Now, how do you actually measure it? Okay. If you have a coordinate plane, an x-y axis, and we're talking about positive angles, if we're talking about degrees, I could have an angle so that my initial side was on the positive x-axis, and then my terminal side was on the positive x-axis, and I never moved at all. And then I would have a 0-degree angle. Okay, it really just looks like a ray. Then, as I move counterclockwise, I'm going to count by 90, because we're going by right angles. So we go 90, 180, 270, and back to 360. So those numbers should be familiar to you. How would that change if we were talking about negative angles? We would still start at 0, but then we would go clockwise to negative 90, negative 180, negative 270, and negative 360. So the difference would be the numbers are now negative. Okay, and then we go around the other direction. Probably the one thing that you need to spend the most time reviewing are then the radians, right? So we don't use the degree sign for radians. If we're talking about moving in a radian, we would start with 0 radians, okay? And then from the animation, we knew that half of the circle was how many radians? Pi. So then this 90 degrees is 1/2 pi, commonly written as pi over 2, okay? Or you might say pi halves, okay? Either of those are acceptable. And so we go from 0 to pi over 2 to pi, and then we know another pi would get us back to 2 pi. What's in between 1 pi and 2 pi? 1.5 pi. Or we would write that most commonly seen as 3/2 pi. Yes. We are going to do the unit circle on Friday. And then we could do the same thing going in the opposite order, right? 0, negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. So the next thing I'm going to do is have you, and you can work in your small groups for this and kind of talk and compare, is graph 4 different angles. I expect the most trouble to happen when we get to the radians. So that's where you need to really be kind of like talking with your group and saying, like, how do you think about it? I'll just preface really quick and say, like, when I'm trying to graph something in radians, I use fractions. I kind of ignore the pi, and I think about, like, 0 to 1/2, 1/2 to 1, 1 to 1.5, 1.5 to 2. Where does the fraction or decimal or whatever I'm working with in my angle measure fit in? And then I can decide which quadrant it belongs in. Okay, so give you a minute or two, see if you can sketch these 3 angles. I'm going to sketch them on 3 different graphs, and I'll walk around and kind of look at what you're doing, and then I'll ask some people to come up here and draw their angles. Talk to your small groups, share some ideas, or compare pictures if you need to. Put your first one on the board. Use a colored pen instead of the black one. Okay. And then Carrie's done when you put your negative 120 on the board here. Okay, if you want to check your first and second one, go ahead and do that, 225 and negative 120. Which quadrant do both of those angles lie in? Quadrant 3. Okay, so we can also identify the quadrant that they're in. And then Bruin, thank you so much, Bruin, has generously gone up and drawn his 3 pi over 7, which I agree with. I think his is in the right spot. It's in quadrant 1. Okay. So I agree with that location of his angle. And what I'd like for you to do is kind of like talk in your small groups, just why did he put his angle right there? Right? Why is the terminal side located in quadrant 1? See if your group can come up with a description that, you know, like makes sense to you. Why is his terminal side in quadrant 1? Go ahead and have that discussion. Okay. April, can you share with us your explanation for why Bruin put his terminal side in the first quadrant?
Because 3/7 is less than 1/2.
3/7 is less than 1/2. Do you agree with that? Yeah, 3 out of 7 is less than 1/2 because half of 7 would be 3.5, right? So to be at the 90-degree mark, or that positive y-axis, we would need 3.5 pi over 7. We don't have that much, so we're not getting that far, and we're going to be stuck in quadrant 1. And that's why I say I use the fractions of pi to help me graph it. Okay? So I like that description a lot. Does anybody else have a different description they'd like to share? I would say this. I'm encouraging you to use that thought process in terms of like the fraction of the whole circle or whole revolution, as opposed to taking a radian and converting it into degrees and then graphing it. I know that that's one way to do it, but since you've already seen radians and degrees once, we're kind of moving forward, and you want to be able to utilize both of them in their realms. So what does that mean for 7 pi over 3? Emily?
7/3 is more than 1. It does an entire rotation, and then goes another 1/3.
Okay, very good. 7/3 is more than 1. It's also more than 2, right? We know that this mark, if we get around 1 full revolution, we're doing 2 pi. Well, 7 divided by 3 is really like 2 and 1/3. So we have to go 2 full pi and then 1/3. So this one should actually be in the first quadrant. And to draw that, you'll probably remember from algebra, you drew like little spirals. Okay, so you go counterclockwise, and you go 1 full revolution and then some. Okay, excellent. If you have any trouble with graphing in radians, I would say this. Try to find 5 minutes to see me before or after school, because I do feel like if you're just having trouble with this, like me being here and Catherine being 5 to 6 feet away from me, it's like something gets lost in translation, right? If you're really struggling with this visually. So come in for 5 minutes, we'll talk about it, and I'm positive that would make a better impact on you than what you're seeing on the board. Okay. Next slide, we want to talk about some different types of angles. So complementary and supplementary, gosh, that's been a long time, right? Anybody quick off the top of their head remember complementary? Jacob? Add to 90. Supplementary? Add to 180. And it should be just 2 angles, not 3 or 4. Very good. Let's add to that radians. What would complementary angles add up to in radians? Pi halves. What would they add up to if they were supplementary? 1 pi. So you can then in your mind, if you can do complementary and supplementary in degrees, you can then kind of like translate that into radians. So if I said, what's the complement of 35? most of you in your head would do like 90 minus 35. So if I say, what's the complement of pi over 3? Just do pi over 2 minus pi over 3. So I'm going to put like a little sort of like cheat here. How do you find the complement? The complement is 90 degrees minus the angle, or you could say pi over 2 minus the angle. Now, we know that negative angles exist. However, negative angles cannot be included in complements or supplements. So if I were to ask you to give me the complement for a 100-degree angle, not possible. 100 degrees is already more than 90, there is no complement. Don't give me negative 10. Okay? So when we refer to complements and supplements, we're referring to positive angles only. Okay? And I could do the same thing with supplementary, 180 degrees minus the angle, or pi minus the angle. So those are not necessarily things that you have to memorize, but they're basically what everyone should be kind of thinking about in their head. And take that total that it's supposed to be and subtract the one that you know. The next pair of angles that we want to talk about are coterminal angles. This one has not been so long, so it's been a while since you've seen complementary and supplementary. Does anybody remember from last year, Algebra 2, what the heck are coterminal angles? Coterminal, Catherine.
So like the angles are the same, except you remember the rotation.
That is a perfect description. Same angle, and I'm going to say different measure. By a difference of one full rotation. And that could be a positive full rotation, so like adding 360, or that could be a negative full rotation, so you could subtract 360. So basically your rule for coterminal angles is add and subtract 360 degrees, or add and subtract in radians 2 pi. Okay. So I'd maybe write that down. Now, if I'm thinking about doing that work in my head, the only thing I'll kind of change about this is you actually want to take the angle plus the full rotation. Thank you. You're going to take the angle plus the full rotation, or the angle minus the full rotation. Whereas like with complements and supplements, you want to put that 180 or 90 first. In coterminal, you really want to put the 360 or minus 360 behind the angle. Okay. Most common mistake I see people do is like take the 360 plus the angle and 360 minus the angle. That won't work for the subtraction one. Okay. So I would write something out like this: my angle plus 360, my angle minus 360, and then that would be like my angle plus 2 pi, or my angle minus 2 pi. And again, I'm going to push you in pre-calculus. If I give you an angle in radians, I really want you to work in radians. I really don't want you to convert it into degrees and convert it back. That's a valid method, but we want to get better at radians. The only way to do that is to work with it. Okay. So here are some examples that I've got. We want to find the complement and supplement, and also coterminal angles, all of the same angle, 2 pi over 5. So again, the idea here is, if I give you an angle in radians, 2 pi over 5, then I want you to think about complements in radians. So I usually think about it in degrees first. In degrees, I know that they would add up to 90. In radians, that means they add up to pi over 2. So I'm going to take pi over 2 minus the angle to get the complement. In order to subtract those, what do you need? Common denominator. So now when you're working in radians, a lot of times you're going to be working with fractions. So you got to follow your correction rules from 3rd grade. Okay. I would get a common denominator of 10. That would be 5 pi over 10 minus 4 pi over 10. And then I get pi over 10 as my complement. Are we okay with my mathematics there? And then if I wanted to do the supplement, of course I'd be thinking 180, but I got to change that because I'm working in radians. So 180 is really pi, so I'm going to do pi minus the angle. So pi minus 2 pi over 5. Certainly you would technically need common denominators here, but I can think about what's 1 minus 2/5. 3/5. Okay, so I don't really do common denominators when I'm doing supplements because that's usually pretty easy. Okay, so 3/5 pi. But certainly you could. 5 pi over 5 minus 2 pi over 5 would be 3 pi over 5. If I switch it up and ask about the coterminal angles, this should be very similar to the directions in Algebra 2. Whenever we asked you to do coterminal angles last year, we asked you, like, get us one positive coterminal angle and one negative coterminal angle. So usually that meant add and subtract. And then sometimes you might have to, like, subtract multiple times so that it actually gets down to the negatives, depending on the size of the angle. So I would take 2 pi over 5, and I would add a full revolution. I would also take 2 pi over 5 and subtract a revolution. Okay, so 2 pi over 5 plus 2 pi, 2 pi over 5 minus 2 pi. This one, maybe common denominators is a good thing, right? Because this is really like 2 pi over 1. So that's 2 pi over 5 plus 10 pi over 5, which gives me 12 pi over 5. And then this is 2 pi over 5 minus 10 pi over 5. So we're at negative 8 pi over 5. I've got one positive and one negative. I'm good to go. Any questions about complements, supplements, coterminals? Okay. Next up is conversions. So you still might need to convert angles, even though I'm saying, like, most of the time if it gives you degrees, work in degrees. Most of the time if it gives you radians, work in radians. However, knowing the conversion is still going to be important. So we need to know what to multiply by if we're going from degrees to radians and radians to degrees. I always think about it like this. If I'm trying to go from degrees to radians, then I'm trying to cancel out degrees. So degrees should be in the bottom of my conversion factor. So then I will put 180 degrees in the bottom, pi in the numerator. Okay? Because I'd be taking like 100 degrees times that pi over 180 degrees, the degrees cancel out. And vice versa. If I want to go from radians into the degrees, I want the radians to cancel out. So I flip my conversion factor so radians are on the bottom. I think most of the time the book will say, like, do the conversion, leave it in terms of pi. So I note that on your gold sheet it also tells you, like, part of your test is calculator and part of your test is no calculator. So, like, conversions would be something I say no calculator for. So, you know, when you do that part of the homework assignment, I would attempt to do it without my calculator. Okay, so leave your answers as like 5 pi over 6. You don't need to multiply by pi. And you want it in that fraction form. Okay, and the last thing. Arc length and area of the sector. This is also something covered last year. Just to give you a quick reminder, we're thinking about a circle. We have a center point, and we have some angle theta. If we're talking about arc length, we're talking like in that animation, the arc intercepted by the angle. So a portion of the circumference. Okay? And we call that S. So S equals R times theta. the radius times the angle. If we're doing area of a sector, then we want to know what is all this space inside that section. So area is 1/2 times r squared times theta. And the rule with those two formulas are theta must be in radians. If you were working in degrees and you didn't want to change it into radians, you would have different formulas. Okay, but I'm going to say use these two formulas and then use an angle in radians. Okay. So I'll say convert degrees first. And that's probably in Algebra 2, one of the biggest mistakes I see in arc length and area of a sector, and it carries over into pre-calculus. I'll still have students who make that same mistake over and over again. So make sure that's something that you study. Theta must be in radians. Okay. So I don't know how much time we have left. It's been 2 weeks, so I can't remember the Wednesday schedule. 1 minute. We don't have 5 minutes.
Get out at 27.
57. Yeah, we're short on time. But this would be an example where it says find the arc length and area of a sector. We just talked about it. Theta is 120 degrees. I'd have to multiply that by pi over 180 and get a fraction 5 pi over 6 before I do that. Please do your homework assignment. Do as many of the problems as you can. We'll go over the answers and any questions that you may have tomorrow. Have a lovely day. It was great seeing you. I'm glad you're back.